Good evening, students, and welcome to this session. In this video, we shall look at sets, indices, and logarithms in our additional mathematics year 1 learner material under section 2. This is your teacher, Sir Isaac, Mathematics Department, Akuse Methodist, Senior High Technical. Introduction. Sets are values expressed in the square roots. Values that are expressed in the square root that cannot be further simplified into whole numbers or integers. So an example of sets are root of 2, root of 3, root of 4. Sets have decimal representations that do not go on forever without repeating. So for an example, root of 2 is approximately 1.4142135. You can check it up with your calculator. So it goes on and it goes on forever without repeating. When we say without repeating, it means that it has no specific pattern. If I pick a decimal like 1.41414141 and so on, here we can see a clear pattern that 4141 is repeating. We call that recurring decimal. So the 41 recurs, and that is repeating. If this happens, the value is not a set. So we are saying that for a number to be a set, its decimal representation has to go on forever without repeating. Let's get the keyword, the phrase, without repeating. An example is root of 2, where we have 1.4142135. If I ask you to predict the next value, you cannot, because there is no clear pattern. It does not repeat. And another example is root of 3, and it can continue in that respect. Root of 5, these are all sets. Now let's look at this activity. Use your calculator to compute the following numbers. So everyone, pick your calculators and compute these values. So let's start with the I, root of 2. Let's take root of 3. And let us also take root of 5. Let's see its decimal representation. So let me also go with my calculator. So the first one is going to be root of 2, and root of 2 is 1.14. So this is the value. This is what I'm getting for root of 2. But one thing you have to take note is that the calculator ends at 4. But you have to know that it continues up to infinity without repeating. So this is the value of root of 2. Let's take the next one, root of 3. So, square root of 3 is giving me 1.7320508076, and it goes on forever. So this is the value of root of 3. It goes on in that respect without repetition. Then lastly, let's look at root of 5. So square roots of 5, and that is the result, which is 2.23606797775 recurring. It goes on and on. So these are the decimal representation of these values. And for the fact that the values reoccurs, no, the value continues, non-terminating. It is non-terminating. It does not repeat. It does not terminate. When we say terminated decimal, 1.414, that is all. I have ended. It means it is terminated decimal. But if I write 1.41, let's see, 1414, where the 14 is repeating, then we call this one repeating decimal, or we call it recurring decimal. And recurring decimals are not sets. For a decimal to be said, that decimal has to be 1, non-recurring. Non-recurring. It means that the value of the decimal value shouldn't have a specific order. It should be non-recurring, and it also has to be non-terminating. So we are saying that a set is 1, non-recurring, and 2, it is non-terminating. Non-recurring, non-terminating. Once these two conditions are met, then that decimal is a set. So example is root of 2, root of 3, root of 5. And you can see that the number goes on forever. And that is the non-terminating part. And if you also look at the number pattern, you can clearly see that the arrangement is randomly mixed, such that you cannot predict the next value, and that is the non-recurring part. Therefore, these values here, these decimals, are non-recurring and they are non-terminating, and that makes it a set. So that should be your observation. Let's look at the next aspect, that is the 2. We have root of 4, we have root of 36, and we have root of 49. Let's look at root of 4. Use your calculator. So let me use my calculator. I have square root of 4, and I have 2 here. That is the answer. Square root of 4, I have 2. So let me take it to the board. 2. So that is the value. Then square root of 36. Square root of 36. I am getting 6. square root of 36 is 6. And that is it. And the last one is root of 49. Square root of 49. Square root of 49. And that is also 7. So we have that here. Square root of 49 is 7. So what is your observation? You can see clearly that with these values, the square root is a natural number or an integer. So what is the distinction between these values and this? We can clearly see that the numbers 4, 36, and 49 are perfect squares. So these numbers are perfect squares. That's 4, 36, and 49. Because 2 times 2 will give you 4. 6 times 6 will give you 36, and 7 times 7 will give you 49. Therefore, these numbers will produce a natural number, and natural numbers are not sets. Therefore, these values are not sets, but these ones are sets. Let's get that clear. Now let us continue. Expressions of the form root of 2, 3 root of 5, and 2 plus root of 7, and so on, that involve or contain square roots of positive integers which are not perfect squares are called sets. So once the element or the number which is under the square root is not a perfect square, then it makes the whole value a set. Once the this a which is under the root sign is not a perfect square, then the whole value is a set. When expressed in decimal form, that sets are non-terminating. I have already explained that. Non-terminating and non-repeating. Non-repeating. So the non-repeating, you can see non-recurring is the same thing. The values do not reoccur. It means that one particular value does not continue to occur or repeat. So it is non-recurring or non-repeating, the same term. And it should also be non-terminating. So once these conditions are met, then it means that that value is a set. Though a calculator with a square root key can give values of set, it must be noted that these values they provide are only approximations. So this is an example. When we picked root of 3, let's take root of 3 again. Square root of 3 or square root of 2, whichever way. So let's say square root of 2. We are getting 1.4142135624. This value is just an approximation because in actual sense, the value is non-terminating. Non-terminating in the sense that it continues forever. It continues forever. So when you come back here, you saw that in our root of 2, we use the 3 dots to indicate that the value continues, non-terminating. All these values are non-terminating. So that is for this. A set is of the form a plus or minus root of b, or root of a plus or minus root of b, where the a and the b are natural numbers. So we can also write natural sets as binomials. That is maybe a natural number plus the set root of 3. This is a set or two sets put together. Example, root of 2 plus root of 3. All these are sets. All these two are sets where the root of 3 shouldn't be a perfect number, where a and b are natural numbers and not perfect squares, is often referred to as a binomial set. So when we say a binomial set, it simply means that a set containing two terms. Binomial means two. So a set containing two terms. The number root of 2 and the root of 3, root of 5, root of 7, and so on are all sets. On the other hand, the numbers where a certain number multiplied itself to give the number is a perfect square. Example of perfect squares are 1, 4, 9, 16, 25. So whenever you have a number 2 and you multiply it by itself, the result is always a perfect square. So think of any number and multiply it by itself. So we can take 10, multiply 10 by 10, and you are going to get 100. So this value 100 is a perfect square. Let's take another number, 12. Multiply 12 by itself, 12, and the result is 144. Therefore, 144 is a perfect square. So you can look out for all the perfect square up to all perfect squares less than 500. You can try that. Check it up. Now let's move on. Let's look at the types of sets. Types of sets. We have what we call the pure sets. A set having only a single irrational number is called a pure set. So example is root of 7, just a single set. Root of 3 is also a pure set. Root of 5 is a set, and root of 2 is also a set, and they are pure set because no number is added to it or is multiplied by that. So it makes it a pure set. Now when we talk of mixed set, a set having a mix of rational numbers and an irrational numbers makes it a mixed set. So for example, there is a rational number 2 and I have an irrational number root of 3. If I combine them or multiply the two, I'm going to have 2 root of 3. So it is a mixture of rational number and irrational number. Therefore, this set is called a mixed set. Another example is 7 root of 2. 7 is a whole number or it is a natural number, and this is an irrational number. So it is a mixture of rational number and irrational number. So therefore, it is a mixed set. Think of more sets which are mixed. Another example is 10 root of 5 is a mixed set. Now let's go to the next one, which is compound sets. Compound sets. Now when do we say a set is compound? A set composed of two sets. A set composed of two sets or a set and a rational number is called a compound set. So an example is a set composing of two sets, that is root of 3 plus root of 10. Two different sets combined is called a compound set, or one rational number and one set. That is, let's say 2 plus root of 10. This 2 is not a set. It is a rational number. The root of 10 is a set. When you combine rational and irrational, it is still a compound set. So these are some examples: two sets combined, or one natural number and one set. So these are examples of compound sets. So you can write 5 more compound sets and add it to it. Now let's go to binomial set. When two sets give rise to one single set, the resultant set is known as a binomial set. So let's get this clear. Let's say we have root of, let's see, 7 times 3. Root of 7 times 3 is going to give us root of 7 3 is 21. So it is from this set that we are getting this. Remember that this set, root of 21, from option 1 is called a pure set. But we can also see that this pure set is coming from the product of 7 and 3, or square roots. Therefore, this 7 times 3, or square root, this is what we call a binomial set. A binomial set. So let's get that clear. So another example is root of 15 times 2. Because root of 15 times 2 can produce a pure set, which is root of 30. So in this case, this is called a binomial set. So think of more binomial sets. So we can take one more. Let me give you one more. Let's say we have root of 25. Or let me say root of 14. If I take root of 14, you can see that root of 14 can be written as root of 7 times 2. So in this case, this root of 7 times 2 becomes a binomial set. So write more binomial sets. Write more binomial sets. Pick any set and write its binomial set. Let's look at this activity 2.2. In a small group or individually, use your calculator to verify the following properties of sets using any numbers of your choice. So let us start with the very first property, the multiplication rules. So the multiplication rule of set states that if you take the set of any number and you multiply it by itself, the answer should just be the square of 1. So that is going to be root of a, or squared. And always the square root and the square symbol are inverse, and the two inverse can always cancel out. So the square root can always cancel the square, and the result is a. An example is root of 3 times root of 3. That must give me root of 3 all squared. And the square root has to cancel the square. So the result is 3. And also take note that that value a must always be greater than 0. Must be greater than 0. Any number under the root sign must always be greater than 0. Let's get that clear. So it has to be greater than or equal to 0. Greater than or equal to 0. Now let's pick another example here. We have another example. Root of 7 times root of 7 is going to give us root of 7 squared. And once the square cancels the square root, the answer is 7. So we are saying that the square of a set is equal to its radical. And the radical is the value under the root sign. So in this case, the 3 is the radical. And that should be the answer. The square of a set, when you square a set, the result is going to be the 3, which is called the radical. So for example, root of 10 all squared will give us 10, where the 10 is the radical, the number under the root sign. Let's go to 2. When you have a set of a given number multiplying a set of another number b, the result has to be the square root of the two radicals multiplied together under the root sign. So we are going to have a times b. So we have root of ab. Another example is if you have root of m times root of n, then the result has to be root of mn. That's it. So now we can use an example. Let's say root of 8, or let's say root of 11 times root of let's say 10. This is going to give us root of 11 times 10, and that will give us root of 110. So we have another examples here. Root of 2 times root of 3 is the same as root of 2 times 3, which is root of 6. And 5 times 11 will be root of 55. So here we are saying that the product of two sets is equal to the set. The product of two sets is equal to the square root of their product, the square root of the product of the radicals. The third rule, or the third property, if you have m root of a times root of a, now here you can see that the m there is any integer, or it is a rational number. The root of a is an irrational number, and that same irrational number is here. So the rule says that pick the two irrational numbers, then you square it. So we are going to have m, then you square the two because they are the same. It becomes root of a all squared. And we have just studied that the square of the square root will always produce the radical, which is a. So the end result becomes a. Then it multiplies the m. So the answer is MA. That is m multiplying a. That is what we have here. So an example is if you have 2 root of 3, so let's say we have 2 root of 3 multiplying root of 3. Here we multiply the two sets, which is root of 3 and root of 3. So we have root of 3 all squared. Then the square root cancels the square, and we are left with 2 times 3. That will give us 6. So let's look at these examples. Root of 3 times root of 3 will give us root of 3 squared, and that will give us 3. Then we pick the radical, the constant here, 5, and multiply it by the 3. So that gives us 15. Another example, we have root of 7, that gives us root of 7 squared, and root of 7 squared is 7. Then you multiply it by this 3 here, and that is 21. Let's go to the next one. M root of A times N root of A. So here you have two different rational numbers. So we have M root of A times N root of, let's say, A. So these rational numbers are different, yet we have the same rational numbers. So the approach still holds. So since we have two rational numbers here, we multiply the 2 as M times N. Then since we have two irrational number sets, we also multiply the 2. But remember that they are the same. Because they are the same, root of A times root of A is the same as root of A all squared. The square cancels the square roots, and we are left with M times N, then times the A, and that gives us M and A, M and A. And that is what we have here. So an example is this. Let's say we have 4 root of 5 times 3 root of 5. So here, multiply the rational numbers, which is 4 times 3. Then also multiply the sets. Since they are the same, it is just root of 5 squared. So 4 times 3 is 12, and root of 5 squared is 5. 12 times 5 is 60, and that is the result. So try hands on this and justify the answer. Let's move on to the next concept. Here we have M times A times root of B. So what is happening here? M root of A times root of B. Here you realize that the sets are different, and there is also a one rational number here. So just hold the rational number, and because the sets are different, the rule says that you just multiply the two and put them in just one root sign. So it becomes root of the product of the two radicals, which is A times B. And we have M root of AB. And that is the result. So an example is you have 3 root of, let's say, 7, then times root of 3. So here, what do we do? Take this 3, which is a rational number. Now, let's focus on this 7 and 3. They are sets. Since they are all set, we can just use one set, that is one square root, and take the product of the two. So 7 times 3. And that gives us 3 root of 21. 3 root of 21. So we can try hands on these ones. Try hands on these ones. We have root of 7 and root of 5. So it becomes root of 7 times 5. Then there is 3 here. So 3 root of 7 times 5. That gives us 3 root of 35. The next one is M root of A times N root of B. So here m root of a times n root of b. Here the rational numbers are different and the sets are also different. So what do? Find the product of the rational numbers, which is m times n. Then also take the product of the two radicals, which is a times b, and put them under the root sign because they are set. So it becomes mn root of ab, mn root of ab. So let's take an example. We have 2 root of 3 times 5 root of 7. Here we can see that the two rational numbers are 2 and 5. So multiply them. 2 times 5. Then the root of 3 and the root of 7 are sets. So take one square root and multiply the radicals, which is 3 times 7. So we have 10 root of 21, and that is the result. That is the result. Let's take this example. We have 5 root of 2 times 4 root of 3. The rational numbers are 5 times 4. So you take the product, then you use just one root sign and multiply the radicals 2 and 3, which is 2 times 3. So 5, 4, we have 20. And we have 2 times 3, which is 6, root of 6. And that becomes the answer to this. Now justify the answer to this one. Now let's go to division rules. Division rules. Root of a divided by root of a. So when you have two sets dividing, what do? We can use the division bar, so we can write it as root of a divided by root of a. And since they are all roots of a radical, we can write it, we can take just one root symbol, then we divide a over a. And we know that a divided by a is 1. Any number divided by itself is 1, provided the a there, that is the denominator, is not 0. So we are going to have root of 1. And root of 1 is still 1. Therefore, the solution to this is 1. And that is what we have there. So we can take an example to be root of 5 divided by root of 5, which can be written as root of 5 over root of 5. And this can be written as root of 5 over 5. And that is the same as root of 1. And root of 1 is 1. So that is the answer. So the rule is that the quotient of two identical sets is equal to 1. The quotient of two identical sets is equal to 1. Is equal to 1. Now let's take the next one. This time we are applying the same property, but the sets are not identical. So we have root of a divided by root of b. The two sets are not identical. We can still write it as root of a divided by root of b. So since they are all sets, we can just apply one root, then a over b. So this becomes the final answer. This becomes the final answer. But remember that the b shouldn't be 0. B must not be equal to 0, because any number divided by 0 is undefined. Let's get that clear. So we can pick an example to be root of, let's say, 11 divided by root of 7. So here we have root of 11 divided by root of 7. That is the same as the square root of 11 over 7. And that is the final answer. That's the final answer. So you can try or justify the answer to this. Let's go to addition rule. Addition rule. So we have m root of a plus n root of a. Now you can see that there is a common set here, root of a, root of a. But we also have some rational numbers here, m and n. So the rule simply says that factorize the common set out. When you factorize the common set out, you are going to get m plus n, then the root of a, which is common set, is factorized out. So this becomes the solution or the rule. So an example is 2 root of 3 plus 5 root of 3. So since the sets are common, we factorize that out. Then we get 2 plus 5. We get 2 plus 5 or root of 3. Root of 3. And that is the answer. Let's try one more. Let's see, we have 7 root of, let's say, 13. Then plus 8 root of 13. Now, since the sets are common, we factorize it out. Then we have 7 plus 8 root of 13. But remember that the final answer, 7 plus 8, becomes 15 root of 13. That is the final answer. So also here the final answer becomes 7 root of 3. That's the answer. Okay. So the same rule applies to subtraction. The same rule applies to subtraction. So let's say we have m root of a minus n root of a. Here too, the root of a's are common, so we can still factorize that out. Then we'll be left with m minus n. So we factorize root of a out to get this. So an example is 7 root of 3 minus 4 root of 3. The answer will be 7 minus 4 root of 3. And we can simplify that to be 3 root of 3. Another one is 10 root of 5 minus 9 root of 5. So here we have 10 minus 9, then root of 5, which gives us 1 root of 5, which can be simplified as root of 5 without writing the 1, because we know that for every set, it is already multiplied by 1. So that becomes the answer. Now let's look at simplification of sets. How to simplify sets. In simplifying sets, you find two factors of the number such that one is a perfect square. This can be done by dividing the number by the prime numbers 2, 3, 5, 7, and so on in 10 as exemplified in the table until you are left with a perfect square, or you divide by a perfect square 4, 9, 16, etc. until you have no remainder. So basically what the note is saying is that, let's say you have been given 8. So let's say you have root of 8. Root of 8, we can simplify root of 8 to get a simplest form. So the question is that, do we have any perfect square that can multiply another number to get 8? Think of it. Yes. If I take 8, it is the same as 4 times 2. And we know that this 4 is a perfect square. So we can now write root of 8 as root of. So instead of writing the 8, I write it as 4 times 2. 4 times 2. Also take note that since the root is affecting the 4 and the 2, we can write them as a binomial, as root of 4 times root of 2, because basically the root sign is affecting the 4 and the 2. And we saw that root of m times root of n can be written as root of mn. So it means that if you also have root of mn, you can also write it as root of m times root of n. So that is the property we are applying here. Therefore, root of 4 times 2 can be written as root of 4 times root of 2. But we know that 4 is a perfect square, and root of a perfect square is just the number, because we know 4. We know that 4 is the same as 2 all squared times root of 2, this root of 2. And we saw that always square root cancels the square. So we are left with 2 here times the root of 2. And that gives us 2 root of 2. So finally, we have been able to write root of 8 as 2 root of 2. And this 2 root of 2 is the simplified version of root of 8. So that is how to simplify a set. That is how to simplify a set. Now let us take the next example. So I'll be picking values randomly from the table. When you take 12, we can also write 12 as the product of 4 and 3, where 4 is the perfect square. When we take 32, we can write 32 as 16 times 2, where 16 is the perfect square. 45 can be written as 9 times 5. 9 is the perfect square. 68 is 4 times 17. 4 is the perfect square. 567 is equal to 81 times 7. The 81 here is the perfect square. And 75 can also be written as 25 times 3, where 25 is the perfect square. So now let's see, we have root of 75 and we want to simplify this. How do we simplify it? So the simplification becomes, how do we write 75 as a product of one perfect square and one prime number? So 75 can be written as 25 times 3. Then we can also write the root of 25 times 3 as root of 25 times root of 3. Then this root of 25 is a perfect square. So root of 25 means root of 5 all squared. The square will cancel this. Then we are left with 5. Then the root of 3 comes there. The root of 3 comes there. So we are having 5 roots of 3 as the answer. So the simplified form of root of 75 is 5 root of 3. So you can try for the rest Let us look at this example. Root of 8. We have already solved root of 8 and we got to root of 2. So we are not wasting time on that. Let's look at these examples. Let me correct the errors here. This is supposed to be root of 18 and this is also supposed to be root of 45. So now you can try them. I'll solve 2 of them and leave the rest for you. So let me start with Ivan, which is root of 108. Root of 108. So root of 108, you have to look for a number, 2 numbers that when you multiply, you will get 108, such that one of those numbers is a perfect square. It's a perfect square. So let's start. Let's say I have 108. Let me start with 108. 108. I want to divide this by first. Let me divide it by 2. I'm getting 54. 54 is not a perfect square, so I don't want 54. So I'll go back and divide it by 3. If I divide by 3, I have gotten 36. 36 is a perfect square. So I have gotten a perfect square. So if 108 divided by 3 is giving me 36, then it implies that 3 times 36 will give me 108. So go back and write 108 as square root of 36 times 3. 36 times 3. Then we can rewrite this one as root of, so we split it as root of 36 times root of 3. And we know that root of 36 will give us 6, because 6 times 6 is 36. So root of 36 is a perfect square, and that is 6. Then it will multiply the root of 3. So that becomes the final answer. That becomes the final answer. Now I will also solve II for you. Then I'll leave the 2 for you as your trials. So let's take root of 18. Root of 18. So we are going to apply the same concept here. Let's go to 18. Let's go to 18. So let's start with 18. Let's divide by 2. Divide by 2. I have 9. This 9 is a perfect square. So straightforward, I can say that 9 times 2 is 18. So we can write 18 as root of, that is square root of 18 as 9 times 2. And that is the same as root of 9 times root of 2. This root of 9 is a perfect square and its value is 3, because 3 times 3 will give you 9, or 3 squared is 9, and the square will cancel the square root, so you'll be left with 3. Then times the root of 2. The final answer is 3 root of 2. That is the simplified form of root of 18. Now take your time and work on this and this. Now let's look at this example 2. This is more of application. So we have a square. A square has an area of 50 centimeters square. So let me use some square here. So let's say I have a square. A square has area to be 50 centimeters squared. What is the exact length in a simplified form of one side of the length? So first of all, you have to know that area of a square is given as L times L, or L squared. And that value, so let's say the length is given as L. So here is also L. So area is given as L squared. But from the question, the area is given as 50 cm squared. So 50 cm squared is equal to L squared. What does it mean? And we all know that L squared simply means that L times L. So the question you ask yourself is that what are the two values that you will multiply to get 50? Two same values that you will multiply to get 50. So to get the value of L, we need to square root here, because if I square root here, the square will cancel the square root by the laws of sets. But once I have square root here, I have to also do the same thing to this. So it means that my L is going to be equal to square root of 50. So we have gotten square root of 50. And we need to find that value, square root of 50. So 50, we know that 50 divided by 2 will give us 25. And 25 is a perfect square. Therefore, 25 times 2 will give us 50. So we can also write that L is equal to root of, instead of writing 50, we can write 25 times 2. 25 times 2. And we can break it down as L is equal to the 25 times 2 can be written as root of 25 times root of 2. So we have L to be equal to root of 25. We know that 5 times 5 is 25. So root of 25 is the same as root of 5 squared, which will give us 5. Then times the root of 2, and we have L to be equal to 5 root of 2. 5 root of 2. Take note that the unit is also squared. So the square will also cancel the square root. Then we will get the unit to be centimeters. So L is equal to 5 root of 2 centimeters. 5 root of 2 centimeters. Therefore, you conclude that therefore the length in its simplified form will be 5 root of 2 centimeters. And that is the length of the square. Now, it is time for you to try these self-assessment questions. So the first question is on a farm scenario, which says that a mixed school farm is marking out a square seed bed for pepper. The seed bed has an area of 72 meters squared. Find the exact length of one side in simplified set form. And the second one is also a general question, which says that a square tile has an area of 98 centimeters squared. Find the exact length of one side in simplified set form. Try these questions. We shall meet next time to continue. Bye bye.